Welcome back to EC 442, 542. Everybody has their mats that I feel like we're back in preschool. So you bring your mat and we can put those down on the floor. Maybe we'll take a nap. But that will be our plane, Z plane, S plane. We'll be thinking now about these different planes. But I've already covered this exam number 1 process in tonight's lecture. I will just let you quickly glance through that and slide through that. I won't necessarily reread that, but you need to bring a sheet of notes and a Z-transform table. I'm not going to be providing you with a Z-transform table. What you will be held responsible for is really everything up through most of tonight's or today's lecture. Homeworks 1, homework 2, and halfway or more through tonight's lecture, everything dealing with frequency response is fair game. Region of convergence, we won't worry about that because that is dealing with inverse Z transforms. We'll do that on exam number 2. Inverse Z transforms. But you should be able to examine some previous exams for practice, and there's topics that are listed on the unit called exam number 1 material on D2L. I'm assuming most of us can, well, I won't say that I can dance, but some of you might be able to dance. So here's a square dance. We have difference equations, which you better be able to move those into a block diagram. You should be able to take that block diagram, and by labeling the outputs of those delay blocks, that will produce state variables, and that will give you a state space representation. You could Z-transform that state space representation to obtain this transfer function, capital G of Z. And whether it's G of Z or H of Z, it doesn't matter. It just depends on my mood, whether I say G of Z or H of Z. But if we've labeled our state space representation in phi, gamma, H, and J, then those appear in the expression for the transfer function, capital G of Z, as H, Zi minus phi inverse gamma plus J. And I've shown a red curve. Those are the ways you need to be able to dance for exam number 1. Going from transfer function to difference equation, that will wait and do on exam number 2. That's the inverse Z transform. But you should be able to follow your way around this 4-cornered square. Question? These slides or these notes will be available after class. So after this review session. I will slide through the first piece, and then we'll slow down and start doing some things a little slower by hand. But here I'm just sort of giving you an overview. I want you to see this diagram and be able to go, oh, sure, I can make these connections. I can go from difference equations to block diagrams to state space to transfer function. Or I can go transfer function to, actually you can go the other way, I guess. Yeah, maybe I shouldn't have said that. You can go transfer function to difference equation, right? You should be able to inverse Z transform these expressions that are Z to the minus 1 times capital Y of Z, Z to the minus 2, capital Y of Z. That's just going to be little y of n minus 1, little y of n minus 2. That will give you a difference equation. So let me change that. I am rethinking my but if I give you a wave or a transfer function, I may not ask you to find what's the time domain waveform. That requires the region of convergence. But going back to a difference equation, you should be able to do from a transfer function. Once you have this difference equation, You should be able to find the homogeneous solution. That's y sub capital H maybe on some previous exams. If you're going, why are you using this crazy notation? A capital H subscript probably means homogeneous. With a homogeneous equation, that means you have zero input, no forcing function. You have non-zero initial conditions. You need to be able to find the solution to a homogeneous equation. If somebody starts exciting that difference equation with some particular input, that will give you a particular solution. You'll also need to find the homogeneous solution and add those two together and find the unknown coefficients by using your initial conditions. And you might want to look at some of the practice problems and try to figure out what I mean by structure of y of n. And that's based on what your particular waveform that you're exciting your system with looks like and what your poles of your transfer function look like. We might get into that in a little bit later. But you should be able to find the structure of the output for a forced and an unforced set of equations. Sampling frequency, or the sample period. How do you find it? What did I say this first equation you needed to remember for at least a few years until you retire, right? Omega sub s is equal to 2 pi f sub s, and f sub s and capital T are reciprocally related. Meaning, if somebody gives you the closed loop bandwidth, omega sub c, 30 times that will give you omega sub s. And from that, you could now find capital T or f sub s, either the sample period or the sampling frequency. Now, what I haven't talked about, and this is what I want to talk about now, is what is the closed loop bandwidth? What is omega sub c? Here's something maybe that was glossed over in earlier lectures. Here is a system, continuous time system. We've now put it into the frequency domain. We're now in the S-plane. Is that system stable? Yes, all of the poles are in the left half plane, so it's stable. How fast do we sample? Omega s is equal to 30 times omega c. Correct. But what is omega sub c in this picture? You have 5 poles up there. Which one? Which of these 5 do we use to determine omega c? Closest to the origin is one answer. Do we have any other answers? What's closest to the origin give us? What is another phrase that we've used for S sub 1? That's closest to the origin in my picture. S sub 2 and S sub 2 bar are conjugates, so they're the same distance away from the origin. S sub 3 and S sub 3 bar are conjugates. They're the same distance away from the origin. We've had one brave individual say that S sub 1 can be used to find omega sub c. But what else do we call S sub 1? How do I illustrate dominant? Have you... How do I dominate somebody? Dominant, it's the, in the S-plane, it's the pole closest to the origin, right? That dominates the behavior. Is that the fastest pole? For the closed loop, here I'm assuming that S1, S2, and S3 are closed loop poles. Which of those are the fastest? That's the one that we need to use to determine our omega sub s, right? We want to find our fastest. Oh, now I gave it away, didn't I? The fastest is the furthest away from the origin. It's not the dominant. It's going to be the fastest. The dominant one is the slowest. That dominates our behavior. S1 will be the one to be the slowest, and that will dominate our response. But we would then need to determine which of these, let's say this is now a hypotenuse R sub 2, and this is a hypotenuse R sub 3. And I'm going to assume that it's not too much of an assumption that the magnitude of S1 is less than the magnitude of S sub 2 is less than the magnitude of S sub 3. And omega sub c is related to that hypotenuse, or the natural frequency, or the magnitude of those complex numbers. If this is the case, then we would say, oh, omega sub c is that radial distance of S sub 3 from the origin. That's the number that we would use for omega sub c. And if this now has a value, let's say that S sub 3 is minus sigma 3 plus j omega sub d, and here is where I may have been too quick before. Maybe I was saying, oh, we use omega sub d. Well, maybe I'll say that that's omega sub d sub 3. I may have gotten in a hurry and said, oh, let's just use omega sub d to determine our sampling frequency. It's really, you could have something that's really far on the real axis that's fast, or you could have something that's really oscillatory near the imaginary axis that's a far away pole, but we're really after the one that's the furthest radially from the origin. And that's the one that we would use for our closed loop frequency to determine our sampling frequency. We want to sample 30 times that fastest pole. And in this case, then, how would we find omega sub c? Well, that would just be this square root of the real part squared plus the imaginary part squared, the hypotenuse. Is that clear? If you now have a transfer function or a system, and somebody says, what's the sample period if you want to find the discrete time system model for that? And you have a circuit that's continuous time, and maybe it has 5 poles, you would be looking at the pole that's the furthest away from the origin to find omega sub c, and then you take 30 times that to find omega sub s. Is that clear? What was S sub 1 again? What did we call this guy? That was the dominant one, wasn't it? And this one, by the assumption, this was the fastest. This one is actually the slowest. And I want you to get that concept in the S-plane, because we'll start talking about that same thing in the Z-plane. Yes? What's determining this 30 times omega c? That's a great question. Does everybody have their ruler? It's a rule of thumb. That's all it is. And we'll maybe demonstrate why that might be important, but it's obviously more than the Nyquist, isn't it? The Nyquist was always twice your highest frequency. Well, we're trying to control the system, not just find information. in our signal. We want to actually, we're more interested in the shape of our waveforms than maybe just whether it's off and on, the information content. So we need to sample faster than the Nyquist, which is twice the highest frequency. We want to capture more than just information. We're trying to control this system. So the rule of thumb is to do 30 times. And we'll maybe talk more about that later, but right now it's just sort of a rule that I'm okay with you using. Was there a second question, or was that the same question? Okay. Worried about our ruler and the thumb. No, you don't like that description? Well, they remembered rule of thumb. Okay. Bounded input, bounded output stability. In the Z-plane, or for discrete time systems, we want our poles inside the unit circle. Where do we want them in the continuous time case for our system to be stable? We want them in the left half of the complex S-plane. We want our real parts to be negative. That gives us an e to the minus something t. That gives us a collapsing or a exponentially damped waveform. Here, having r's or radiuses inside the unit circle, that gives us collapsing also exponentially, because when we raise a number less than 1 to a higher and higher power, what happens? Please answer before I get too low. It shrinks, doesn't it? That's why I don't run backwards anymore. Other questions? Equations of motion. You should be comfortable finding the equations of motion for a circuit, for a mechanical system, for an electromechanical system, and how do you use that? How do you put those into a state space representation? Z-transforms. You should be able to Z-transform a generic function of little n, a time domain signal. You should be able to Z-transform a difference equation and find a transfer function. You should be able to take an all-delay block diagram and put that into the frequency domain and then find a transfer function from that if you want. In the time domain, what do our delay block? In the time domain, what are our block diagrams consisting of? What are the dynamic blocks? These, right? Delays, unit delays. In the frequency domain, those are z to the minus 1. Z transforms. You need to be comfortable with those. Transfer functions, you need to be able to find those either using block diagram algebra, Z-transform the difference equation, the formula to connect the state space time domain representation to a transfer function. You need to be able to apply all of those. And phi, ideally, I'd love to be able to give you a 5 by 5 phi. I probably won't give you anything more than a 2 by 2. So you should be able to invert symbolically a 2 by 2 matrix. Yes. You don't have to, but it might impact your grade. Okay? I think you're flipping a coin if you take that chance. Settling time determination. When does a settling time determination even make sense? Now I'm in the Z-plane. Under what conditions is it even reasonable to talk about settling time. The poles have to be stable, don't they? They have to be inside the unit circle. If you don't have a stable system, you can't settle. You're not going to be talking about a settling time. Is that clear? Now, if you have multiple poles floating around, how do you determine the R? Here I have R sub 1 and R sub 2. Which R would I use to determine the settling time? Okay, you pull out your quarter and you flip it, right? You have two choices, R1 and R2, 50-50 chance, but since you are here, pardon me, you flipped your coin and you said 1. I don't know if I'd want that coin. I'd want either heads or tails, but 1, R sub 1, I assume, is what you're suggesting. How many think it's R sub 1? Show of hands. How many think it's R sub 2? How many aren't thinking? Which one is the which poles are dominating the behavior of your system? Now what's our relationship between Z and S? Z is equal to e to the st. What were we looking for S values that dominated? Where were those S's close to? The origin, S equal to 0. If we plug in S equal to 0, what does Z tell us? Z equal 1. Now we need to be close to Z equal to 1 to be dominated. And if it's settling time, we need to be inside the unit circle. Now, which of these pole pairs is closer to Z equal 1? R sub 1. This R sub 1 is dominating the behavior. That's the slowest pair of poles. R sub 2 collapses more quickly. Let's just give it a number. Let's say it has a radial distance of 1/4, and R sub 1, let's say, is 3/4. So you have 3/4 compared to 1/4. Then you square them. Which one's collapsing quicker? You then had 1/16 versus 9/16. Then you cube it, right? So now you have 4 cubed in the denominator, and the appropriate 27 over 64 versus 1 over 64. The 1/4 is shrinking more quickly, correct? That's the faster pole. This is the dominant, or slowest. This set is the fastest. So, which R? R1 would be used for the settling time. Is that clear? If I gave you a transfer function, you would find the roots of its denominator, and you would find the R's that were, they all need to be less than 1, and then you would find the R that's closest in magnitude to 1. And we'll just use that. In fact, R sub 1 and R sub 2 actually play nice together, and R sub 2 helps R sub 1. But we, in this class, let's just pick one, and we'll pick the one that's closest to Z equal 1 for giving us something to play with. Questions on that? Now we're going to, speed up but slow down. Does that make any sense? So now let's find a state space representation, because I want to go home and make sure my alarm goes off at 3 a.m. Okay? That's one reason for keeping your phone somewhere else in the other part of the house, right? Then you probably lose it, and I don't have a search button on my phone. Somebody will have to call my phone. Never mind. Find a state space representation for the given difference equation. Suppose that somebody gives you the following. Y of n is equal to 1.4 y of n minus, y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus u of n minus 2. What's the order of this difference equation? How many think it's first order? No, what I need to do, I'm playing wrong, aren't I? Show me one finger, two fingers, or no fingers if... High five. All right, on the count of 3, show me which fingers you think it is for its order, system order. Okay, 1, 2, 3. Should be 2. We have 2 delays, and in this case, what we want to do then is end up with a block diagram that has 2 delay blocks. This was one of your homework problems because now we have delays in our input, which is different from what we talked about in class. And let me show you a technique that I didn't discuss in the hint for homework solution, or for homework number 2. So here's another construction approach. If that technique didn't seem to make any sense, let's look at a different one. And in this one, I'm actually going to nest delays, if that makes any sense. To make this construction, I'm going to assume that I have access to the output y of n and the input u of n, or that those are available for me to use. And I'm going to say that D, the letter capital D, is my delay operator. With that, I want to now rewrite y of n in terms of y of n and u of n and delay operators. Meaning, if I delay y of n by 1 delay, I end up with y of n minus 1. Meaning, I now can delay the 1.4 y of n, and I actually have the 1.4 y of n minus 1. Is that okay? I also have a u with that same index, time index, u of n minus 1. So let me just say I now have u of n. And that, those two terms account for those two pieces on the right-hand side of my difference equation, because I'm now delaying both of those with a unit delay. Now what I want to do is nest another delay. So let me now say that's in addition to delayed version of, and now I want to account for this piece and that piece. What? Pardon me? You don't like my brackets? It's not a Final Four bracket, or how's that? Is that a little bit better? Oh, if you're going to ask me to match, I'm opening another bracket. Humor me. Now I'm going to try to do something with blue, meaning I now have a minus 0.45 y of n. So that term gets delayed twice. It's delayed here with that funny bracket, and delayed here with the first bracket, or delay. Is that clear? I haven't yet closed my curly bracket. I don't know what I'm going to call that bracket. One, wrong. Okay, the class wants that to be the wrong bracket, but I'm going to have to close that wrong bracket in a minute, hopefully sooner than a minute. And I also need to delay the input, the blue input, and now I'll close that bracket. Isn't that beautiful? And I'll close this other bracket. Just for that, I'm going to widen my paper. So now I have everything on the right-hand side that I had before. Is that okay? And all I'm using now are delays and Y's and U's without delays in their arguments. But do you see that what I've bracketed on the right is equivalent to the original difference equation? Now what I want to do is put this into a block diagram. So I said that I have these signals Y and U available to build with. So what I'm going to now do is say, okay, I have a U of N and I have a Y of N. And I now need to create Y of N out of delayed versions of Y and U. And the first one that I'm going to do now is going to be, whoops, I didn't want to do that. I wanted to make that kind of a bracket. The wrong bracket. So this is going to be the input to the very first delay block. Meaning I now have a delay block right here, and I want to make as an input U of N and minus 0.45 Y of N. And that now gives me right there. That gives me star. And if I delay that, coming out, I'm now going to add to that the next two terms that go into a delay block. Meaning now I need to come out of here and have those go into a delay block. And now all of this needs to create the input